This is a set of tutorial videos using FLAC3D to calculate the total and effective stresses for a homogeneous embankment dam with rock abutments. This set of tutorial videos provides an extension of the FLAC2D tutorial embankment dam that had modeled the problem to the left. In these new set of tutorials in FLAC3D, a more complex geometry, shown to the right, will be modeled. Note that the geometry of the embankment dam and the stream direction modeled in FLAC3D will be the same as the tutorials in FLAC2D. In addition, the properties of the embankment dam remain essentially the same. The additional geometric complexities that will be modeled in FLAC3D are highlighted here. In this new model, the crest width of the dam will be 3 embankment heights, and the channel width will be a single embankment height. The adjacent rock abutment and foundation will be modeled with 20 feet of foundation rock below the embankment, and 15 feet of rock abutments to the right and left. This set of tutorial videos have been developed to incrementally lead to calculating the total and effective stresses of the complex geometry shown, and have been broken into 3 parts. In the first of these 3 tutorial videos, the command script in FLAC2D was modified for FLAC3D, and a numerical mesh that includes a 65-foot width of embankment was used. The numerical mesh of this model, Model 1, was developed with extrusion with sketch set. In the second video of the 3, the steps to develop the numerical mesh of the more complex geometry to the right using building blocks was presented. The numerical mesh of this model, Model 2, includes the embankment with the rock abutments. In this last tutorial video, the numerical mesh for Model 2, created in the previous tutorial, with modifications of the analysis script for Model 1 given in the first set of tutorials, will be used to calculate the total and effective stress of the embankment with the rock abutments. Please note that for both numerical meshes, the models have been developed to have less than 1,000 numerical zones and therefore can be completed using the free demonstration mode version of FLAC3D available. Before presenting the analysis commands for conducting the analysis, let us first reopen the project file with the saved numerical mesh from the previous tutorial. The numerical mesh can be opened by the following set of graphic-based interactions. Now that we have ensured that numerical mesh from the previous tutorial is viewable, it is now time to present the analysis commands. Although many of the commands used for the analysis for Model 2 are used to analyze Model 1, there are several noteworthy changes and/or additions, and therefore instead of just highlighting edits only, the entire command script for each data file will be discussed. In discussing these data files, the commands will be presented with customized syntax highlighting and figures to help connect FLAC3D commands to the analysis of Model 2. A similar set of data files as in previous analyses were used. 1_ static analysis, in which the total stresses of the dry embankment are computed. 2_ seepage analysis, in which the pull water pressures are computed with the reservoir. And 3_ update stresses, in which the effective stresses and densities are updated. Note that for this relatively simple mesh, the flow through the drain was not explicitly modeled, and therefore the computation of water flow in 3_ flow calculations was omitted. Let us now revisit the data file 1_ static analysis, for which the total stresses are computed for the dry embankment. The first command provided, model new, will ensure that the analysis is beginning with a new model. With the new model, the numerical mesh created in the last tutorial with building blocks is restored with the command model restore mesh.save. This analysis is configured for mechanical and fluid fall calculations, with the latter option specified using the model config fluid command. Constitutive models that relate stresses to strains are now assigned. For this analysis, the isotropic elastic model will be used for the embankment, drain, and rock zone groups. The command zone C model elastic without range group command may be used here because the same constitutive model is applied to all zone groups. The material properties for the zone groups will be specified. The properties for the embankment are the same as before. Mass density 3.73 slugs per cubic foot. Shear modulus 3.73 times 10 to the 6 pounds per feet squared. Bulk modulus 6.23 times 10 to the 6 pounds per feet squared. These values are specified to the embankment zone group with the command zone properties density 3.73, shear 3.73 e to the 6, bulk 6.23 e to the 6, range group embankment. For the rock abutments and foundation, it is expected that the material stiffness should be notably larger than the embankment. In this analysis, the stiffness is selected to correspond to a shear wave velocity of 3,280 feet per second, a value that is over 3 times that of the shear wave velocity in the embankment. With the rock then, with a Poisson's ratio of 0.35 and mass density of 4.35 slugs per cubic foot, the shear modulus equals 4.68 times 10 to the 7 pounds per feet squared, and bulk modulus equals 1.40 times 10 to the 8 pounds per feet squared. The density and stiffness are assigned for the rock using similar commands as the embankment. In this analysis, the actual blanket drain is not explicitly modeled, but instead a row of numerical zones beneath the downstream toe of the embankment. In addition, because of the need for a simple numerical mesh with less than 1,000 numerical zones, the zones for which the drain material is assigned are in a region that would have normally been rock. Because of these simplifications, any impacts of different mechanical properties of the drain on the total stresses are not intended to be captured. For the sake of simplicity then, the stiffness and density properties in the drain material will be the same as the rock. The density and stiffnesses are assigned for the drain using similar commands as the other two materials. Boundary conditions are now specified. Using the zone group faces in the default slot, the zone face group bottom is fixed in the X, Y, and Z directions. The two sides contained in the zone face group side are fixed in the Y direction, and the zone face group front and back are fixed in the X direction. In specifying these boundary conditions, the range command is included with specifications of one or more zone group face names. Gravity is specified, and next, to mimic a dry embankment, the saturation is initialized to 0. The last step is to set a few key analysis settings. 1. Model fluid active off to turn off fluid flow calculations. 2. Model mech active on to turn on mechanical calculations. And 3. Model large strain off to turn large strains off. Static equilibrium is determined using the model solve command. Once the solution is found, the final step is to save the state. The next data file, 2_seepage analysis, will be discussed now, where the pour water pressures due to the reservoir will be computed in the embankment, drain, and rock. The first command in the data file will be model restore 1_static_analysis.sav, so that the previous save state is restored. Next, we specify the fluid constitutive model. As before, the anisotropic fluid constitutive model will be used for the embankment zones and is specified with the zone fluid C model anisotropic range group embankment command. For the drain and rock, the simpler isotropic fluid constitutive model will be used and is assigned in a similar fashion as with the embankment. The value of the horizontal and vertical permeabilities in the embankment is the same as before and is assigned with the command provided here. For the drain, a permeability much larger than the embankment is used, that is a mobility coefficient of 1 times 10 to the minus 7 feet per pound for feet squared times seconds. And for the rock, a permeability much smaller than the embankment was used, that is 1 times 10 to the minus 13 feet per pound per feet squared times seconds. The assignment of permeabilities in the drain and rock is similar to that of the embankment. The fluid density of water of 1.94 slugs per cubic foot is specified next using the zone water density 1.94 command. Now for the initial conditions. Reasonable estimates of initial conditions will help in ensuring an accurate solution. Here, the pour water pressure is initialized as hydrostatic below the embankment. This initial condition is assigned with the command zone grid point initialize pour pressure with the following additions. 1. The pour water pressure changes by minus 62.4 pounds per feet squared per foot as we move vertically upwards with a maximum value of 1,248 pounds per feet squared. And 2, this initial condition is only specified below the embankment, that is z equals minus 20 feet to z equals 0 feet. Since in this material the pour water pressures are non-zero, the saturation should be initialized to 1. This is achieved with the zone grid point initialized saturation 1.0 range position -z minus 20 minus 1 e to the minus 4 command. Note that z equals minus 1 e to the minus 4 and not 0 here, so that the top of the node at z equals 0 was not assigned a saturation of 1, but 0. Next up are the external boundary conditions. Along the upstream slope, the maximum value of pour water pressure occurs at the upstream toe and is equal to the height of the reservoir water times the unit weight of water. With a height of water of 60 feet, the maximum pour water pressure is equal to 3,744 pounds per feet squared. with the pore water pressure changing by minus 62.4 pounds per feet squared per foot as we move vertically upwards. The pore water pressure continues to decrease vertically upwards until the reservoir surface at z equals 60 feet is reached. This surface, for which the variation in pore water pressure applies, has been predefined and corresponds to the boundary 1 zone group face within the fluid slot. Specification of the pore water pressure along the surface is achieved with the command zone face apply pore dash pressure 3744.0 gradient 0,0 minus 62.4 range group fluid equals boundary 1. Along the downstream boundary, it will be assumed that the pore water pressures will remain as hydrostatic. The surface in which this condition will be assigned corresponds to the boundary 2 zone face group within the fluid slot. Ensuring that the pore water pressure remains hydrostatic could be achieved by fixing the pore water pressures, or as shown here, applying the pore water pressures using a command that is similar as that for boundary 1. The goal with the drainage material is to achieve a dry, near zero pore water pressure condition in the adjacent embankment material. This condition can be modeled by fixing the pore water pressures to zero along the drain embankment surface. This drain embankment interface corresponds to the boundary 2 zone face group within the fluid slot, and the command to fix the pore water pressure is shown here. The remaining two parameters that will be specified are the fluid bulk modulus and fluid tension. As done in the previous tutorials, the fluid bulk modulus is set to 100 pounds per feet squared and the fluid tension to 0. We are now almost ready to conduct the steady-state seepage analysis. An uncoupled analysis will be conducted in which the steady-state seepage will be determined without changes in effective stress. This analysis setting is achieved with the following commands. 1. Model fluid active on to turn on fluid flow calculations, and 2. Model mech active off to turn off mechanical calculations. We can now solve for steady-state seepage using the model solve ratio-flow 1.0 e to the minus 3 command. Once the solution is found, the final step is to save the state. The last data file is 3_update stresses. In this data file, the effective stresses and density will be updated. For the data file 3_update stresses, the commands used are almost identical to this version of the analysis as in the first FLAC3D tutorial. In fact, only two changes are required. The first change required is that the data file 2_seepage calculations is restored instead of 3_flow calculations. The second change required is that the surcharge pressure is assigned to the boundary 1 zone face group within the fluid slot and not upstream 1. All of the commands shown here are the same. Once the set of commands for 1_static analysis, 2_seepage analysis, and 3_update stresses have been typed and saved, click the green arrow or simply click Ctrl E for each file. First, 1_static analysis, 2_seepage analysis, and finally 3_update stresses. You will see a cycling info dialog box open that presents the results during cycling. The analysis results from FLAC3D for each analysis step can now be reviewed and assessed with a series of plots. A highlight of a few of the plots that could be created in FLAC3D are now shown. This completes the last part of the three-part tutorial calculating the total and effective stresses of a homogeneous embankment dam with rock abutments. This analysis presents the beginning of many more complex analyses, such as the analysis for gravity-driven instability, rapid drawdown, and earthquake-induced deformations, all common analyses in dam engineering practice.